Today we will see another binary tree problem, and it's finding the maximum width of binary tree at any level of this given tree. So this problem has multiple versions, and earlier what I thought it was slightly different from that. So I thought that maybe I need to count the number of nodes at each level and return the maximum of such values. So in that case we would have returned 2, since none of the levels have more than 2 nodes. Here we have 2 nodes. But this problem was slightly different. So here, even if some nodes are absent, you have to fill in those nodes. So here we will not fill it, since this is after the last node. But in between, so you need to consider the first node and the last node at a given level. And you have to assume that the missing nodes are present. So the width here will be 3. Since this position is empty or it's null. But we will not add here. Similarly, if this left child was missing but 2 was here as the right child, then we would have not filled this left. Then the width would have been 2. So let's see an example here. So here we have width of 1. Here we have width of 2. All the nodes are filled. There is no empty node. So at any level, we can have 2 raised to the power that many of empty spaces. So if you make a complete binary tree and fill all the nodes, then you will have something like this. So you just need first and last. So let's say first is this, last is this, then it will be 3. Similarly, if first is this and last is this one, then here it will be 1, 2, 3, 4, 5, 6. So width here will be 6, even if these nodes are absent, or even if some nodes in between are absent, still this width is 6. So you got some idea, but how we will solve it? If we just do simple BFS, then we will be inserting this in the queue. Then when we pop it, we will be inserting 3 and 6. And now queue size will be 2. So we will get a size of 2. Next, for the next 2 elements, that is 3 and 6, we will pop them and also insert their children into the queue. So we will again insert 2 and 4. So we will never get more than 2. So what we will do, instead of simply pushing the nodes, we will also assign an index to them. So if you have worked with, if you have implemented binary heap, then you must be aware of this, that a binary heap is a complete binary tree, and at the last level some nodes may be empty, and these are left shifted as possible. So here what is the index? It's at index 1, it's at index 2, 3, 4, 5, 6, 7, and so on. So we can implement a binary heap using array, because we know that all these intermediate levels are filled, only last level is not filled. So if this is index 1, then the index of its left child will be, left of a node at index idx will be 2 times idx, and right will be 2 times idx plus 1. So 1 times 2 is 2, twice of 1 plus 1 is 3. Then its double is 4, and you see index 4. Then 4 plus 1 is 5. So there is a difference of 1 here. Similarly, double of 3 is 6, and this index is 6, and this one is 7, and so on. So even if these nodes are not present, we know their indices. So what we will do, we will assign an index of 1. You can also start with 0. Let's assign 0. Then the formula will slightly change. So 0, 1, 2, 3. This is absent, 4, 5th, 6th is also absent. So here the formula is that it will be twice plus 1, and this is twice plus 2, because we started from 0. So what we can do, we insert not just node but also its index. So in that way we will know that the first element is at position 3, last one is at position 5, and in between we have to fill anyway. So using these two values we can find the width. 3 to 5, that means 3, 4 and 5, that is 3. So let's run through this example. So we insert 5 and 0 into the queue, and the queue is not empty, so we will continue. So if root is empty, that means there is no node, so result will be 0. But if root is not empty, root is there, then at least width will be 1. So we initialize result with 1. Then we pop this 5, 0. So 5 is the root node, the tree node, and 0 is its correct position. And then we look at the size of queue. So size is 1, so we will pop one element and insert them into the queue. So we will insert 3, 3, 1 and 6, 2 into the queue. Now the size becomes 2, so we know that these are the nodes at the same level, so we will process 2 of them. So we calculate size beforehand. This is just normal BFS. So we pop 3 out of this, and at this point, when we are finished with one iteration, we will see that what is the first element, what is the last element. So what is the index of first element? 1. Index of last element is 2. So what is the difference or width? It's last minus first, that is 2 minus 1 plus 1. So here it will be 2. So we got a better result. So we will also check result equal to max of existing result and end index minus start index plus 1. So here result will become 2. Next, again it's not empty, it will pop 3 and insert its left, that is 2 with an index of 3. Its right is empty, so it will not insert it. Next it will pop 6 and its child is 4 with an index of 5. Right is empty, so it will not insert. Now this queue has 2 elements. Now again we will check what is the first index, it's 3, last index it's 5. So result will be max of existing result, that is 2, and 5 minus 3 plus 1 is 3. So result now becomes 3. And then we will pop it, there is nothing to push, both are empty. Similarly we will pop it and finally return this result. So I hope this is clear. Let's try to write this in C++ and Python. There is no node in this tree, so return 0. Then if root is there, then result initialized to 1. Then queue pair tree node star, and second one is index starting from 0. You can also use make pair, but you can use this initializer list. Start is the start index, and this second value in this pair denotes that index. First is the tree node. So IDX of this node is the second element of this pair. So we will use this for while inserting its children. So the index of its left child will be 2 times IDX plus 1, and index of right child will be 2 times IDX plus 2. So if left is there, then push it into the queue. And what should be the index? 2 times index plus 1. So IDX is the index of current node. Similarly for right one. And finally here we will return result. So it's not end is the iterator. It should be back, front and back. And this works for this case. So let's try a few more cases. So this denotes this tree. So if we make this 3 null, then it will be 5 here and 9 here. So that should be again same answer, 4. And you can see the tree being drawn here by LeetCode. This is a cool feature. So 3 is here. When we make it null, it will be gone. So you see this 3 is gone. Still it should be 4. This is the left child of this. This is the right child of this. So let's run it. And it's 4. So let's submit. And we run into some signed integer overflow at line 29. So this 2 times IDX is overflowing the limit of signed integer. So we see that the indices are growing exponentially. So let's look at this. Let's look at one example. So let's say we have this tree. Let's take a general tree. At level 1 we have starting from 0. So 0, 1, 2, then 3, 4, 5, 6. So at this level we are consuming one index, one of the integers. Here we are consuming 2. Here there are 4 nodes. Here we will have 8 nodes, 16, 32, and after some time you see that it's becoming a huge number. So in general it's 2 raised to the power level number. So it's exponential. Here it's 2 raised to the power 0. So with a few number of nodes, let's say even if we have a sparse tree like this, then we are checking for left and right. Let's say we have something like this. It's not increasing, but we have just 2 nodes at each level. But this is the leftmost node and these are the rightmost nodes. So all the intermediate nodes indices will be consumed even if they are not present. So we'll be assigning the correct indices. So it will be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So you see that even if nodes are absent, we are consuming that many number of indices. And quickly after 32 level, you can see that the number of nodes will be 2 raised to the power 32, or even after 31 levels, it will be 1 plus 2 plus all the way up to 2 raised to the power 31. So we will consume the int max limit. Similarly, even if you use long and you decide to use 64 bits, still after 63 levels, all those values will be consumed. So what we will do here, we will do some optimization. So once we are processing nodes level wise. So we processed this one and then we popped it out and then we pushed next level nodes. Then we processed all of these and pushed next level nodes. So we are only working with one level at a time, or you can say two levels at a time. So when the iteration ends, then strictly there is all the nodes in the queue are of one level. So we will start popping them and start pushing their children into the queue. So we are only bothered about two levels at a time. So once we are done with this, what we can do, we know that the first index is 3 here and the next index is 6, last index. So does it matter if the indices are from 3 to 6 or is it from 0 to 3? If we keep this distance, or if we offset all of these indices, decrement them by fixed amount, it does not change anything. And here the indices are 7 to, let's say it's 6, so 14, it's 7 to 14. So what will happen if I make it 0 to 3 instead of 3 to 6? It will be twice of this plus 1, that is 1, twice of this plus 2, that is 8. So if we make it 0 to 3 instead of 3 to 6, so it was earlier 3 to 6, we made it 0 to 3, then its children, index of this will become 1 and index of this will become 8. We have to double it and add 1 for left, and we have to double it and add 2 for right. So again you see that here the difference is 7, here also the difference is 7, and in the next level also it will propagate like this. So once we are done with a level, we will reset it. So we will take the first index as 0 always. So let's say it's starting from 1024 and this index is let's say 2048. I am putting some random number. This will be not like this. One of them will be odd, one of them will be even. So here it will become 0. So we will decrement everything by this beginning index. So it will become 0, and from here also we will subtract this. So it will become 1025. So it will be 1025 instead of 2048, and this will be 0 instead of 1023. So this we will do for preventing that overflow that was happening. We were keeping track of all the previous values which we don't need to. So let's update our solution. So you see we are subtracting this start from IDX so that it will automatically be reflected here. And this solution is accepted. There is no overflow. And we are around here. Most of the solutions are concentrated here only. Now let's write it in Python. And inserting this should be same as inserting here only. Q dot first means Q0 and second of this means index 1. and the Python solution is also accepted.